Look up at a dark night sky and it feels complete. Thousands of stars hang above you in a glowing river. It is easy to believe that band is the whole universe. In truth, you are seeing only a thin slice of it. Every point of light belongs to a vast spiral city of stars. We call that city the Milky Way, our galactic home. Tonight we will leave our tiny neighborhood and ask where the sun truly sits inside it. If you enjoy journeys like this, tap like, subscribe, and explore the galaxy with us. From Earth, under a truly dark sky, far from city lights, you can see roughly 6,000 stars with just your eyes. That sounds like a lot until you remember that our galaxy holds hundreds of billions of stars. For every star you can see, there are tens of millions you cannot see. They are too faint, too distant, or hidden behind drifting clouds of dust. The sky that feels full to you is actually almost empty. Every one of those visible stars is a local. They all belong to our Milky Way. That faint milky band that cuts across the sky is not fog and not a cloud. It is the edge-on view of the galactic disk, seen from the inside. A galaxy is a gravitational city made of stars, planets, gas, dust, and an invisible backbone of dark matter. Our city happens to be a spiral, with arms that curl around a bright central hub. And our city is not alone. Astronomers think there may be around 100 billion galaxies in the observable universe, maybe more. Between them stretches an enormous darkness called intergalactic space, filled with a whisper-thin gas. When you stack that scale against the few thousand stars you can see by eye, Earth shrinks from a world into a speck. Our whole solar system becomes a tiny apartment in one building of one city in a universe full of cities. So, where is that apartment? Start small. The solar system is built around the Sun, a fairly ordinary yellow star. 8 major planets orbit it. There are moons, dwarf planets like Pluto, rocky rubble in the asteroid belt, and a wide disk of icy debris farther out. On a simple diagram, it looks clean and tidy, circles around a dot. In reality, it is a 3-dimensional swarm of worlds and rock and ice, all locked to the Sun by gravity. To talk about its size, astronomers use the distance between Earth and the Sun as a basic step. They call that 1 astronomical unit. Mercury sits well inside that step, Mars is roughly 1.5 steps out, and Jupiter is more than 5. Far beyond Neptune lies a broad ring of frozen leftovers called the Kuiper Belt. It stretches from about 30 to 50 astronomical units from the Sun, a vast mine of comets, ice, and rock. If you could hover above the solar system, you would see a bright inner family surrounded by a dim, cold halo of debris. All of this is wrapped in something you cannot see at all. The Sun constantly blows out a stream of charged particles called the solar wind. That wind drags the Sun's magnetic field with it and carves out a bubble in the surrounding space. That bubble is called the heliosphere. It is like an invisible force field surrounding the Sun, the planets, and the Kuiper Belt. Inside it, the radiation environment is shaped by our star. Outside it, the galaxy takes over. The space beyond that bubble is not truly empty either. It is filled with the interstellar medium, the very thin stuff between stars in the Milky Way. Most of it is extremely diffuse hydrogen, plus dust grains, energetic particles called cosmic rays, and giant clouds of gas cold and dense enough to form new stars. Those clouds are the nurseries, where future suns and future planets will be born. At the boundary where the heliosphere pushes against this medium, space becomes more like weather. Pressures balance, flows bend. Nothing is quite simple anymore. As the solar wind races outward, it eventually begins to slow as it pushes into the interstellar medium. There is a region where it drops from supersonic speeds to slower, more tangled flow. That change of state is called the termination shock. Beyond it lies the heliosheath, a thick, turbulent shell where the solar wind continues to lose speed and energy. Farther out still is the true frontier, the heliopause. That is the place where the outward push of the solar wind and the inward pressure of the interstellar medium meet and balance. The heliopause is not some neat wall. It is a shifting, wrinkled boundary, about 11 billion miles from the Sun in most directions, roughly 18 billion kilometers. Inside it, most of the high-energy cosmic rays from the galaxy are deflected or softened. Outside it, the radiation and particles belong to the Milky Way itself. Without this magnetic bubble, life on Earth would have grown up under a far harsher shower of radiation, if it could have evolved at all. Right now, you, me, everyone you know, and everything humans have ever built, live deep inside this moving bubble, orbiting a fairly ordinary star. We have not yet sent a human being to its edge. For almost all of our history, we did not even know the bubble existed. Yet this thin magnetic skin and its position inside the galaxy have shaped the story of life on Earth. Later in this journey, we will follow the first machines that reached that frontier and stepped into interstellar space. For now, hold this picture in your mind. A tiny glowing system, wrapped in an invisible shield, drifting through the vast, dark ocean of the Milky Way. In the late 1970s, we quietly threw 2 glass bottles into the cosmic ocean. Each bottle carried music, images, greetings in dozens of languages, and a golden map that says where we live. We named those bottles Voyager 1 and Voyager 2. For decades, they drifted outward on the wind of the Sunday. Then one of them finally hit the edge of our protective bubble and slipped into true interstellar space. Voyager 1 launched in 1977. It stole gravity boosts from Jupiter and Saturn, and then kept going, riding the solar wind into the darkness. For more than 30 years, it surfed that invisible flow inside the heliosphere. Around 2012, it crossed the heliopause, the shifting frontier where the solar wind gives up and the interstellar medium takes over. From that moment on, every particle and field around it belonged not to the Sun, but to the Milky Way. That crossing did not look dramatic. There was no wall, no flash of light, no sudden view of alien stars. What changed was the music in the background. Instruments on Voyager 1 saw the density of charged particles jump. The direction of magnetic fields shifted. Cosmic rays from the galaxy surged. It was as if the spacecraft had moved from the quiet inside of a house to a windy street outside, even though the scenery still looked like deep black sky punctured by distant points of light. Follow that direction a little farther, and you meet our closest true neighbors, the Alpha Centauri system. From Earth, it looks like a bright single star in the constellation Centaurus in the southern sky. In reality, Alpha Centauri is a triple system, 3 suns locked in a slow gravitational dance. 2 of them are sun-like stars that circle each other every 79 years. The third is a tiny red dwarf on a much wider, slower orbit. The 2 main stars are called Alpha Centauri A and Alpha Centauri B. A is slightly bigger and brighter than our Sun, with around 1.1 times the mass and about 1.5 times the luminosity. B is a little smaller and cooler than the Sunday. From far away, they blend together into one point of light that is among the brightest in our night sky. Closer in, each star would have its own sky, its own habitable zone, its own chance at worlds with liquid water. The third member, Proxima Centauri, lurks farther out. It is the closest star to the Sun, at roughly 4.2 light-years away. Proxima is a red dwarf, by far the most common type of star in the galaxy. It is about 7 times smaller than the Sun, and a little more than half as hot. In size, it is only about 50% larger than Jupiter, yet it has enough mass and pressure in its core to fuse hydrogen and shine on for trillions of years. Red dwarfs like Proxima burn their fuel slowly and are incredibly long-lived, but they are not gentle. Proxima is a flare star, which means its magnetic field can snap and unleash enormous bursts of energy. In 2019, it produced an ultraviolet flare that briefly grew tens of thousands of times brighter than normal in that wavelength. For any planet nearby, these tantrums mean intense radiation storms sweeping across the sky, again and again, day after day. That is the environment any life would have to survive in. Despite that, Proxima Centauri has at least 3 known planets. The most famous, Proxima b, orbits in what we would call the habitable zone, the band of distances where liquid water can exist on a rocky surface. It has a mass a bit higher than Earth and circles its star in only 11 days at a distance of about 0.049 astronomical units. That is more than 20 times closer to its star than Earth is to the Sunday. At that distance, it is almost certainly tidally locked, with one face always staring into the red glare and one face in eternal night. The tides there would be brutal. Gravity from the star would stretch the planet and pull on its atmosphere. Some models suggest the tidal forces in the air could be hundreds of times stronger than the ones that move our oceans. Yet the climate might still settle into something stable, with winds carrying heat from the day side to the night side. It is possible that liquid water pools in a ring around the terminator, the line between light and dark. It is also possible that flares and radiation strip the atmosphere away and leave a dead, frozen rock. Right now, we simply do not know. Farther out in the system is Proxima c, a mini Neptune with a mass around 7 times that of Earth. It orbits Proxima at roughly 1.5 astronomical units, taking about 1,900 Earth days to complete a lap. Its temperature is likely far below freezing, closer to deep outer solar system values like -230 degrees Celsius. Even farther in is Proxima d, a light little world with around 1/4 of Earth's mass, whipping around the star in only 5 days at a tiny fraction of Earth's orbital distance. Together, these worlds turn our nearest star into a compact, complex laboratory for studying exoplanets. There is even evidence for a planet in the habitable zone of Alpha Centauri A, a candidate known as C, one that might be a mini Neptune or a super-Earth at about 1.1 astronomical units. Put all of this together, and it becomes very tempting to ask a simple question: could we ever live there? Could we ever send probes that return close-up images and hard data instead of distant spectra and wobbles in starlight? That is where reality hits with a thud. Alpha Centauri is our next-door neighbor in galactic terms, but it is still more than 4 light-years away. That is about 23.5 trillion miles, or nearly 38 trillion kilometers. The retired Space Shuttle Discovery topped out around 17,500 miles per hour. At that steady speed, a trip to Alpha Centauri would take roughly 148,000 years. Even the faster Voyager spacecraft, moving at over 35,000 miles per hour, would need tens of thousands of years just across a couple of light years and hundreds of thousands of years to reach the star itself. Future crew capsules like Orion may fly a bit faster, but not enough to change the basic picture. With rockets that push hot gas out the back, the journey is simply too long for human lifetimes. So we stand here in a strange position. On one hand, we can map the nearest stars, weigh their planets, estimate their climates, and even watch flares explode on their surfaces. On the other hand, they remain utterly out of reach, for now. This tension between what we can see and what we can touch is one of the driving questions of modern space exploration. In the next part of our journey, we will look at one bold idea that tries to close that gap and send a swarm of tiny starships racing toward Alpha Centauri within a single human generation. So, if rockets are far too slow, what does it actually take to chase a beam of starlight? One answer sounds like pure science fiction. Shrink the spacecraft until it is the size of a postage stamp. Give it a thin, reflective sail, only a few meters wide. Then hit that sail with an enormous laser and let light itself shove the craft toward Alpha Centauri at a significant fraction of the speed of light. This is the basic idea behind Breakthrough Starshot. Forget giant starships with sleeping crews and spinning habitats. Think of a swarm of gram-scale probes, each one a tiny chip packed with cameras, sensors, and a radio. Each chip is attached to an ultra-thin sail made of reflective material. On Earth, an array of many individual lasers fires upward, combines its beams, and pushes that sail from far below. Light carries momentum. When photons bounce off a mirror, they give it a tiny push, Under normal sunlight, that push is minuscule. Under the focused glare of a powerful laser array, it becomes enormous. Starshot imagines a square kilometer of lasers working together for only a few minutes at a power level comparable to the entire electrical usage of a major country. For that short burst, each probe would be hammered by a storm of light. If everything works, the sail and chip would be pushed up to around 20% of light speed. That is more than 130 million miles per hour, or over 200 million kilometers per hour. At that speed, a probe could cross the 4+ light years to Alpha Centauri in roughly 20 years. Then, a few years later, its signals would arrive back at Earth. Instead of waiting tens of thousands of years, we could see real images of another star and its planets within a single human lifetime. The challenges are brutal. Earth's atmosphere bends and distorts light, which makes it hard to keep the laser focused on a sail that starts a few hundred kilometers up and quickly races away. The sail has to be incredibly light, yet strong enough not to tear under the intense pressure of the beam. The electronics must survive huge accelerations. Even a grain of dust in space could smash a probe moving at that speed. There is also no obvious way to slow down at the destination, so the craft would blaze through the Alpha Centauri system in a quick flyby. Yet the concept matters even if the details change. Starshot forces us to rethink what a starship looks like. It shifts our imagination from giant metal cylinders to fast, disposable, robotic seeds. Instead of sending one grand ship every few centuries, we could one day send flocks of tiny scouts, knowing that most will fail, but a few will succeed. It is a very different way of thinking about exploration and about our relationship with nearby stars. Meanwhile, whether we go to them or not, those stars are not standing still. The local neighborhood of the Sun is a slow-motion swarm. Every star has its own orbit around the Milky Way's center. Some move almost alongside us. Others cut across our path. Over millions of years, their positions change like grains of dust in a stirred pond. Take Barnard's star. It is the second closest stellar neighbor after the Alpha Centauri system, an old red dwarf about 6 light-years away. On the sky, it has the largest proper motion of any star, which means its position against the background shifts more quickly than any other. Over just a human lifetime, it creeps a noticeable fraction of the apparent width of the Moon. That fast motion tells us it is sliding by relatively nearby in galactic terms. Barnard's star is ancient, perhaps twice the age of the Sun, and for a long time astronomers assumed it was quiet. Then, in the late 1990s, it surprised observers with a powerful flare that briefly made it much brighter in blue light. Even elderly red dwarfs can still throw tantrums. We eventually found at least one planet there, a cold super-Earth that circles close in yet still probably sits in a deep freeze because the star is so dim. Now look at a very different neighbor, Sirius, the dog star. It is about 8.5 light-years away and shines more brightly than any other star in our night sky. Sagittarius A is a hot, massive star that would outshine the Sun many times over if you put them side by side. It also has a faint white dwarf companion, Sagittarius B, the collapsed core of a star that has already gone through a red giant phase and died. Together they show how varied even a small patch of the galaxy can be. On longer timescales, some stars do more than drift past. They dive in close enough to brush against the very edge of our solar system. Far beyond the Kuiper belt lies the Oort cloud, a vast halo of icy bodies stretching perhaps a light year from the Sunday. When another star swings near that halo, its gravity can jostle those distant comets, nudging some of them onto new paths. We know this has happened in the past. A small dim system, often called Schultz's star, appears to have passed close to the Oort cloud tens of thousands of years ago. In the future, another star, often labeled Gliese 710, is expected to come within a fraction of a light year in about 1.25 million years. It will not threaten Earth directly, but its pull could send fresh waves of comets raining slowly into the inner solar system for millions of years afterward. So, our local region of the Milky Way is not a static postcard. It is a dynamic stage where stars age, flare, pass by, and occasionally shake the deep frozen outskirts of our planetary system. Breakthrough Starshot imagines reaching one of those stars quickly. Nature is already running a much slower, but much larger, experiment with all of them at once. In the next part of our journey, we will zoom out again and see the bigger structure this neighborhood moves through. A vast carved-out cavity in the interstellar medium, called the local bubble, and a nearby stellar nursery where new suns are being born. Imagine pressing pause on the motion of the stars and drawing a giant invisible sphere around the sunday. Not a sphere of rock or metal, but a region of slightly denser interstellar gas, softly glowing in X-rays. Our solar system is not just drifting through emptiness. It is moving through a kind of cosmic scar, a bubble carved into the galaxy by ancient explosions. Astronomers call it the local bubble, and right now we are traveling inside it. The local bubble is a cavity in the problem. Interstellar medium, roughly 1,000 light-years across, stretched into an odd peanut-like shape. It appears to have been hollowed out millions of years ago when clusters of massive stars in our region of the Milky Way exploded as supernovae. Their shock waves swept gas outward, heating and thinning the interior, and piling material up along the edges, like overlapping blast craters in slow motion. Inside this cavity, the gas is thinner and hotter than average. Around its surface, where the blasts shoved matter together, dense clouds have formed. Those clouds are where new generations of stars are being born. The sun did not start inside this bubble. For a long time, it orbited farther away. Then about 5 million years ago, it wandered into the cavity, like a ship sailing into a huge, calm patch of ocean left behind by an old storm. Nested within the local bubble is another structure called the local interstellar cloud, sometimes nicknamed the local fluff. This cloud is a patch of slightly denser, cooler gas, roughly 30 light-years wide. Right now, the solar system is moving through it. That gentle background environment matters. The density and temperature of the gas and dust around us can change the size of the heliosphere, the level of incoming cosmic rays, and perhaps the long-term conditions for life on Earth. From our point of view on the inside, we cannot step back and photograph the entire local bubble. We infer its shape from how gas glows in X-rays and ultraviolet light, from how starlight is absorbed, and from the positions of young star-forming regions along its rim. When astronomers map those clues, they see arcs of newborn stars and nebulae traced along a shell. Our local space is not random. It is structured by past violence and ongoing creation. One of the most dramatic nearby sites of creation sits in a familiar pattern of stars, the constellation Orion. Almost everyone in the world who can see the night sky has seen Orion. His outline is made from a bright reddish star at the shoulder, a bluish star at the opposite knee, and, most famously, 3 stars in a straight line across the middle that form Orion's belt. Those 3 belt stars are hot, massive supergiants that burn bright and die young. The red star at Orion's shoulder is Betelgeuse, a red supergiant roughly 650 light-years away. If you replace the sun with Betelgeuse, its swollen atmosphere would reach beyond the orbit of Mars and maybe into the asteroid belt. It is about 700 times the size of the sun, and many times more luminous, yet its surface is cooler, which is why it glows a deep orange red. Inside, it is burning heavier elements and approaching the end of its life. For years, astronomers and the public have wondered when Betelgeuse will explode as a supernova. When it finally does, its outer layers will blast outward at tens of thousands of kilometers per second, while its core collapses into an extremely dense object, either a neutron star or a black hole. From Earth, the explosion would rival the brightness of the full moon and be visible even in daylight. That sounds dramatic, but in reality, it is very unlikely to happen in our lifetimes. On stellar timescales, it may be due to explode soon. On human timescales, soon could still mean 100,000 years. Drop your gaze just below Orion's belt, and you find something softer, a small sword-shaped smudge that looks like a fuzzy star to the naked eye. Through binoculars, it becomes a glowing cloud. Through a telescope, it reveals dark lanes, bright knots, and a swarm of young stars. This is the Orion Nebula, one of the closest and most active stellar nurseries in the Milky Way. It is about 1,300 light-years from Earth and spans 30 to 40 light-years across. The Orion Nebula is a vast cloud of gas and dust, lit from within by newborn stars. Its apparent brightness is around magnitude 4, which means that under a clear, dark sky it is just visible to the unaided eye. Inside the nebula, gravity has pulled gas together into dense knots that collapse and ignite nuclear fusion, turning into fresh stars. Many of these stars are only 1,000,000 years old, infants on the cosmic timeline. Some are still surrounded by thick disks of dust that may one day clump into planets. At the center of the nebula is a tight cluster of hot young stars, called the trapezium, named for the way 4 of its brightest members form a distorted diamond. Their intense ultraviolet light carves cavities in the surrounding cloud and makes the gas glow. That radiation also sculpts and erodes nearby disks, perhaps influencing which planetary systems survive. Deeper observations suggest there may even be a relatively massive object hiding in the cluster, possibly a black hole formed from an earlier generation of stars. Recently, the James Webb Space Telescope turned its infrared eyes on the Orion Nebula and peeled back even more structure. By looking at wavelengths that cut through dust, it revealed hundreds of so-called planetary mass objects, some with masses similar to Jupiter. A few of them seem to travel in pairs, 2 Jupiter mass bodies orbiting each other without any star at their center. These strange, free-floating binaries challenge our tidy categories for planets and stars. Are they failed stars? Are they planets that were kicked out of their birth systems? The nebula is full of such questions. What makes the Orion region so powerful in this story is that it links directly back to our own history. The Sun and its planets likely formed in a similar stellar nursery billions of years ago, inside a giant molecular cloud shaped by earlier generations of stars and explosions. The local bubble itself may be the fossil of that process, carved by siblings of long-vanished suns. When we look at Orion, we are seeing not just a pretty pattern, but a time machine, a snapshot of the kind of environment that once gave birth to us. So our current neighborhood is a layered structure. The solar system sails through the local interstellar cloud, which sits inside the broader local bubble, whose walls host active star-forming regions like Orion. Above us, Betelgeuse is nearing its eventual death, while below Orion's belt, baby stars are lighting up for the first time. This is the living skin of the Milky Way, full of scars and nurseries. In the next part of our journey, we will step back even farther and see how these pieces fit into the grand design of the galaxy's spiral arms, and where exactly our sun sits inside that enormous rotating disk. If you could fly far above the Milky Way and look down from millions of light-years away, you would not see a random cloud of stars. You would see a shining pinwheel. At the center, a bright bar of stars stretches across the core. From the ends of that bar, 2 great spiral arms sweep outward, filled with gas, dust, and suns in all stages of life. Somewhere out in one of the smaller branches of that pattern is a modest yellow star, dragging a handful of rocky worlds and gas giants along for the ride. That star is our Sunday. For a long time, we did not know this. From inside the disk, the Milky Way looks like a pale band wrapping around the sky. Early astronomers drew maps of the stars they could see and argued about the rest. It took radio telescopes and infrared observatories to cut through the dust and trace the real skeleton of the galaxy. By following clouds of hydrogen gas and counting newborn star clusters, we discovered that the Milky Way is a barred spiral galaxy, not a simple pinwheel with 4 equal arms, but a more complex structure where 2 main arms dominate. Those 2 big arms are called Scutum, Centaurus, and Perseus. They begin at the ends of the central bar and coil around the galaxy like 2 broad highways. Between them lie smaller, patchier arms such as Norma and Sagittarius, more like side roads and interchanges, than main routes. The major arms are rich in both young and old stars, as well as dense clouds where new stars are forming. The minor arms are more gas-heavy, with scattered pockets of star formation. Our Sun does not live in one of the main highways. It sits on the edge of a smaller spur named the Orion Arm, sometimes called the local arm. This is a modest branch that stretches perhaps 10,000 to 20,000 light-years in length and a few thousand light-years across. The Orion Nebula, many of the bright stars of the winter sky, and our entire solar system all share this same minor arm, like neighbors along a side street off a busy galactic avenue. From the galactic center, our Sun lies about 26,000 light-years out, roughly halfway between the core and the outer edge of the disk. That position is more than just a coordinate. It sets the backdrop for everything that happens on Earth. Closer in, toward the central regions, stars are packed more tightly together. Supernovae, intense radiation, and chaotic gravitational encounters are more common. Farther out, the disk thins, and there may be fewer heavy elements available for building rocky planets. The Sun and its planets orbit the center of the Milky Way the way Earth orbits the Sunday. The numbers are just much larger. One full lap around the galaxy takes about 250 million years. Astronomers call that a galactic year. The Sun has been shining for about 4.5 billion years, which means it has completed somewhere between 18 and 20 orbits since it formed. Dinosaurs walked the Earth when the solar system was on a very different side of its path than it is today. To complete that circuit, the solar system moves at an astonishing speed, roughly 220 kilometers per second, which is close to 1% of the speed of light. At that pace, it still needs around 1,400 years to travel a single light year. In 8 days, it moves about 1 astronomical unit, the same distance that separates Earth from the Sunday. We are hurtling through the galaxy at high speed, while also spinning around our star and turning on our axis, yet from the ground our world feels stable. The spiral arms themselves are not solid structures that drag stars along like the arms of a windmill. They are more like traffic waves on a busy highway. Cars move in and out of the dense regions, but the jam pattern itself can stay in roughly the same place for a while. In the same way, stars move through spiral arms over time. The bright, knotty arms we see are patterns where gas compresses, clouds collapse, and massive young stars light up before they quickly burn out. That detail matters, because spiral arms can be dangerous neighborhoods. Massive young stars die as supernovae, blasting out high-energy radiation and shock waves. Dense star fields mean more close encounters between stars and any planetary systems they host. If a star spends too much time plunging through these arms, any planets in its habitable zone may be bombarded by more frequent extinction-level events. The galactic disk may have its own version of a habitable zone, just as stars do. Our Sun appears to be in a relatively calm region between the most crowded parts of the arms. Its orbit keeps it far enough from the galactic center to avoid the worst of the chaos there, while still close enough in that the interstellar medium is enriched with heavy elements from earlier generations of stars. That combination may be rare. Many stars in the Milky Way follow orbits that carry them repeatedly through the densest parts of spiral arms. Some calculations suggest that a large majority of stars might have environments less stable than ours over long stretches of time. When you put all of this together, our address looks something like this. We live in a planetary system inside a magnetic bubble called the heliosphere. That system orbits a yellow star. The star is part of the Orion Arm, between the major Scutum Centaurus and Perseus arms. The Orion Arm sits in the outer half of the Milky Way disk, which is wrapped around a bar and a central bulge that contain a supermassive object at the core. That disk, in turn, floats inside an invisible dark matter halo. It is easy to feel lost in such a structure. Yet there is also a quiet comfort in realizing that our Sun occupies a kind of cosmic suburb, not too crowded, not too empty, metal rich enough for planets, but far from the fiercest fireworks. This may be one reason complex life had time to emerge and evolve on Earth. In the next part of our journey, we will leave our safe neighborhood and visit some of the true giants of the galaxy. Stars so large that they make the Sun look like a glowing pebble, and ask what happens at the extreme upper limits of stellar size. Up to now, the Sun has been our measuring stick. It is easy to think of it as big because it dominates our sky and its gravity holds the planets in place. Yet in the wider Milky Way, the Sun is not a giant. It is a middleweight. Out there are stars so large that if you swap them in for our Sun, they would swallow most of the solar system. To really feel the scale of the galaxy, we need to stand next to one of those monsters. Meet Scuti. It sits in the constellation Scutum, about 10,000 light-years away. On a star chart, it does not look impressive. Through a small telescope, it is just another faint reddish speck. On the scale that matters, though, it is one of the largest known stars in the Milky Way. If you could put Scuti where our Sun is, its bloated atmosphere would reach far beyond the orbit of Jupiter. In terms of radius, Scuti is roughly 1,700 times larger than the Sunday. That gives it a diameter of more than 8 astronomical units, 8 times the distance from Earth to the Sunday. Think about the volume that encloses. You could fit more than 1 million Earths inside the Sunday. Inside a sphere the size of Scuti, you could cram billions of suns. This is what a true hypergiant looks like. Here is the twist. Scuti is huge, but it is not especially massive compared to some other stars. Its mass seems to be only around 7 to 10 times that of the Sunday. Meanwhile, another star, with the somewhat clunky name R136A1, weighs in at roughly 300 times the mass of the Sun, yet has a radius only about 40 times larger than the Sunday. One is a swollen balloon, the other is a compact furnace. This highlights an important point. When astronomers talk about a star being massive, they mean how much matter it contains, not how physically big it is. Mass shapes the gravity, the pressure in the core, and the rate at which a star burns its fuel. Radius tells you how far that hot gas has puffed out into space. Hypergiants like Scuti have relatively modest masses for their gigantic sizes. Their outer layers are loose and extended, like a foggy atmosphere barely held in place. Despite their size, these stars are not the hottest objects around. The surface of Scuti is actually cooler than the Sun, almost half as hot. That is why it glows a deep red rather than white or blue. Most of its energy leaks out over a huge area, so every patch of surface can be cooler while the total luminosity remains enormous. Closer to the core, in the deep interior, temperatures soar as heavier elements fuse, and the star creeps toward the end of its life. Scuti is also a variable star. Its brightness changes slowly over time. Those fluctuations come from unstable tug-of-war between gravity pulling inward and pressure from nuclear fusion pushing outward. Layers of the star can swell and contract like a breathing lung. As they move, the temperature and brightness seen from Earth shift. By studying these changes, astronomers can learn about the internal structure and physics of the star, the same way a doctor learns about a heart by listening to its rhythm. Hypergiants do not live long. Their huge, extended envelopes are fragile. Strong stellar winds blow mass off into space. Pulsations and eruptions can fling gas away in great arcs. Around Scuti, astronomers see a vast nebula of material that the star has already shed, stretching hundreds of times the distance from Earth to the Sunday. That cloud is both a sign of the star's instability and raw material for future generations of stars and planets. Any planets that once orbited close to a hypergiant like this would almost certainly be gone. As the star swelled during its evolution, its outer layers would have engulfed the inner orbits. Worlds that survived farther out would face wild changes in radiation and stellar wind as the star pulsed and blew off shells of gas. The quiet, steady illumination that Earth enjoys from the Sun is not a given everywhere. Around giants, stability is a luxury. Eventually, a star like Scuti will run out of options in its core. After fusing heavier and heavier elements, it will reach iron, which cannot be used to generate more energy through fusion. When that happens, The core will collapse under its own gravity, and the outer layers will be blasted outward in a titanic supernova. What is left behind will likely be a neutron star, a city-sized ball of ultra-dense matter, or possibly a black hole. The nebula surrounding it will glow as the shock wave races through the gas it has already lost. So on one end of the spectrum we have hypergiants, fragile, swollen, shedding mass, and racing toward explosive ends. On the other end are small red dwarfs that sip their fuel and can shine for trillions of years. Our sun lives somewhere in between, massive enough to be bright and stable for billions of years, not so massive that it burns out in a cosmic heartbeat, and nowhere near large enough to threaten the outer planets. Once again, our star turns out to be quietly special. These extremes also set the stage for something even stranger. Because when you pile enough mass into a small enough space, you do not get a bigger star at all. You get a tear in space-time. At the very center of the Milky Way, far beyond even the largest hypergiants, there is an object with millions of solar masses squeezed into a region smaller than our own solar system. In the next part of our journey, we will dive toward that dark heart, Sagittarius A, and ask what really lurks at the core of our galaxy. So far, our journey has wandered through a quiet galactic suburb, spiral arms, local bubbles, stellar nurseries. To understand the Milky Way as a whole, though, we have to visit its downtown. At the very center, the star fields grow dense, gas clouds tangle, and gravity rules every move. Buried inside that crowded core is an object so extreme that it bends not only the paths of stars, but the fabric of space and time itself. We call it Sagittarius A. Sagittarius A is not just one thing. The name covers a complex region in the constellation Sagittarius, where our line of sight toward the center of the galaxy passes through thick walls of dust. Inside that cloudy chaos sits a bright, compact radio source, often written as Sagittarius A star. That tiny radio dot is where the real monster hides. From its pull on nearby stars, astronomers infer that it packs about 4 million times the mass of the Sun into a region smaller than our solar system. On paper, that description screams black hole. A black hole is a place where so much mass is crammed into such a small volume that escape velocity exceeds the speed of light. Light cannot climb out, so the object itself is dark. Around the black hole there is a boundary called the event horizon. Anything that crosses that boundary is gone from our visible universe. We can never see inside. We can only watch what happens to matter and light outside that limit. At the galactic center, we cannot see the black hole directly, but we can track the stars that race around it. Near Sagittarius A, there are so-called S stars that whip through tiny orbits at thousands of kilometers per second. Some complete an entire ellipse in a few decades. By following those paths, astronomers can weigh the central object the same way you can weigh a hidden planet by how its moons move. The answer is always the same: millions of solar masses. Very little space. No sign of a normal star cluster that could survive there. Matter that falls toward this central mass does not plunge straight in. Gas and dust spiral inward, forming a flattened structure called an accretion disk. Friction and magnetic fields inside the disk heat the gas to millions of degrees. At those temperatures, the gas emits X-rays, infrared light, and radio waves. Telescopes tuned to those wavelengths see a flickering ring around the invisible core. The disk is the dinner plate. The black hole is the hungry guest in the middle that we cannot see. The Event Horizon Telescope, a network of radio observatories spread around Earth, uses a technique called very long baseline interferometry to act like a planet-sized dish. In 2019, that collaboration released the first image of a black hole shadow in another galaxy. A few years later, they did the same for Sagittarius A. The picture did not show a sharp hole. It showed a glowing ring of radio emission with a darker patch in the center. Exactly what theory predicts when hot gas orbits close to an event horizon and light is bent by intense gravity. Even more intriguing, Sagittarius A is not just massive. it is spinning. Physicists describe black hole spin with a parameter they call A, which ranges from 0 for no spin up to 1 for the maximum possible spin. Observations of X-ray and radio emission suggest that Sagittarius A has a spin between roughly 0.84 and 0.96. In plain language, it is rotating very fast, close to the theoretical limit. Spin changes everything. A spinning. Black hole drags spacetime around with it. Near the hole, there is a region called the ergosphere, where space itself is being twisted. Inside that zone, nothing can remain still relative to distant stars. Everything is forced to co-rotate. This effect, known as frame dragging, alters the paths of particles, and even the paths of light. Photons that skim close to the event horizon can loop around the black hole before escaping, producing rings and arcs of light and creating the dark central shadow seen in the Event Horizon Telescope images. There is a strange beauty here. Despite the enormous difference in scale between Sagittarius A and the much larger black hole in the galaxy M87, their images look surprisingly similar. The underlying physics scales with mass in such a way that the basic pattern of ring and shadow persists. It is as if nature uses the same blueprint for black holes of many sizes. Yet even in this apparently tidy picture, there are puzzles. One of the most famous involves a cloud of gas and dust called G2 that passed very close to Sagittarius A few years ago. Many astronomers expected that as the cloud neared the black hole, it would be torn apart and heated, producing a bright flare. Instead, G2 seemed to stretch a little and then drift past with much less drama than predicted. Follow-up work suggested that G2 might hide a compact star at its core, which would help it survive. Still, the encounter raised questions about how matter behaves in the extreme environment near the event horizon. Puzzles like that have encouraged some researchers to explore more radical ideas. What if the mass at the center of the Milky Way is not a classic black hole at all? One proposal imagines a very dense clump of dark matter, built from unknown particles that interact only weakly with light. In that picture, the core of the galaxy would be a kind of dark matter star, still incredibly compact, still exerting the same gravitational pull on nearby stars, but without a true event horizon. Simulations show that a massive ball of dark matter could, in principle, mimic some of the dynamical effects we attribute to a black hole. It could reproduce similar stellar orbits. It might even explain some details of how gas flows near the center. Those ideas remain speculative. The majority of evidence still points strongly toward a true supermassive black hole, especially when we consider the broader population of active galactic nuclei and the way their jets and disks behave. But in science, even dominant models have to survive constant testing. What we can say with confidence is this: there is a compact object at the heart of the Milky Way, with millions of solar masses. It sits inside a crowded nuclear star cluster. It feeds only occasionally, flaring when a clump of gas wanders too close. It spins rapidly, twisting space-time in its vicinity and bending the paths of light. Whether it is exactly the textbook black hole of general relativity or something even stranger, it is the anchor of our galaxy. Around that anchor, the rest of the Milky Way organizes itself. Gas flows inward through the disk. Some of it eventually reaches the central regions and feeds the core. Stars in the bulge and bar orbit under its influence. Dark matter in the halo holds the entire structure together on the largest scales. In the next part of our journey, we will zoom out from this central monster and map those larger components, from the bright stellar disk and bulge to the ghostly halo of dark matter that outweighs everything we can see. Stand back from the galactic center, and the Milky Way begins to look less like a simple pinwheel and more like a layered machine. There is a thin, bright disk where most of the stars live. There is a swollen central bulge wrapped around the supermassive object we just visited. There is a faint, extended halo of ancient clusters. And surrounding everything, there is something even stranger, an invisible shell of matter that does not shine at all. We did not always know this. In the early 20th century, Astronomer Harlow Shapley mapped the positions of globular clusters, those dense balls of hundreds of thousands of stars that orbit the galaxy. On the sky, they did not form a neat circle around the Sunday. They formed a swarm centered in the direction of Sagittarius. From that pattern, Shapley realized two key things. The Milky Way is far larger than earlier astronomers believed, roughly 100,000 light-years across. And the Sun is not at the center. It sits off to the side, closer to the edge than to the middle. What Shapley saw were the outer workers of a deeper structure. At the heart of the Milky Way is a rounded bulge of stars, almost spherical in shape. This bulge is made mostly of older stars that astronomers label population 2. They tend to have low amounts of elements heavier than helium. Their orbits are random and elongated rather than neatly circular. Around this bulge stretches the flat stellar disk, the part we see from Earth as that hazy band across the sky. The disk is where most of the galaxy's visible stars live. It is only a few thousand light-years thick, but tens of thousands of light-years in radius. Inside it, there is a mix of ages. The youngest, most metal-rich stars live in the spiral arms, glowing blue and white. Astronomers call these population 1 stars. They contain more of the heavy elements that earlier generations forged, including the silicon, iron, oxygen, and carbon that make up planets and people. Their orbits are well organized, almost circular, and they stay close to the galactic midplane. Some of these population 1 stars gather into loose associations called open clusters. Unlike globular clusters, which are dense and ancient, open clusters are fragile. Their stars are only lightly bound by gravity. Over time, the tides of the galaxy tear them apart and scatter their members across the disk. Our Sun probably began life in such a cluster, then drifted away as its siblings slowly spread out. Older disk stars blur the line between the flat component and the bulge. Some have slightly eccentric orbits that carry them a few thousand light-years above or below the plane. Their metallicity is lower than that of the youngest stars, perhaps a tenth of the Sun's heavy element content. Together, these populations trace the gradual chemical enrichment of the galaxy as one generation of stars lives, dies, and seeds the next with new ingredients. Beyond the disk and bulge lies the stellar halo. This is a huge, sparse sphere of stars and globular clusters that surrounds the visible galaxy out to hundreds of thousands of light-years. Halo stars are among the oldest in the Milky Way, with ages between 10 and 13 billion years. Their orbits are wildly tilted and elongated, crisscrossing the disk and plunging far above and below it. As a group, the halo barely rotates at all, compared to the disk's ordered spin. The globular clusters Shapley used as beacons belong to this halo. They swarm around the galaxy's center like bees around a hive. Inside each one, hundreds of thousands of stars move in a crowded dance. Their low heavy element content tells us they formed early, before the Milky Way had time to enrich itself. Many halo stars may actually have been born in smaller galaxies that were later swallowed and shredded by the growing Milky Way. The halo is full of such fossils. There is also a halo of hot gas extending far beyond the visible disk, with a diameter of several 100,000 light-years. X-ray observations reveal that this gas can hold as much mass as all the stars in the galaxy combined. Embedded within it are streams and shells that trace long-ago collisions. When astronomers look at the motions and chemistry of halo stars, they see evidence that the Milky Way has already merged with many smaller galaxies and is still accreting their remnants. Underneath all of these visible layers lies an even more massive one. Roughly 9/10 of the matter in the Milky Way does not emit light. This dark matter does not glow, does not absorb, and does not scatter photons the way ordinary gas and dust do. We know it is there because of gravity. Stars in the outer parts of the galaxy orbit faster than they should if they were feeling only the pull of the visible disk and bulge. If there were no dark matter, orbital speeds would drop with distance from the center. The way planets in the solar system move more slowly, the farther they are from the Sunday. Instead, the Milky Way's rotation curve stays almost flat. Stars far from the center move nearly as fast as those closer in. The simplest explanation is that they are moving through a huge, roughly spherical halo of unseen mass that extends well beyond the visible disk, possibly out to around 2 million light-years. Dark matter also helps keep the thin disk stable. Its extra gravity deepens the galaxy's potential well, holding on to fast-moving gas and stars that might otherwise drift away. Simulations that include only normal matter struggle to grow realistic spiral galaxies. Simulations that include dark matter halos naturally produce systems that look much more like the Milky Way, with extended disks, rotating bars, bulges, and halos of debris from past mergers. So when you think of the Milky Way, picture more than the bright band of stars you see on a clear night. Picture a rotating disk laced with spiral arms. Picture a central bulge wrapped around a supermassive object. Picture globular clusters arcing far above and below the plane. Then wrap all of that in an enormous, invisible halo of dark matter that outweighs the shining parts many times over. The galaxy we can see is only the luminous skin of a much larger structure. Those layers are not just abstract components in a textbook diagram. They record the life story of the Milky Way. The bulge and halo remember its early years and ancient mergers. The disk and spiral arms map its ongoing star formation. The dark matter halo provides the stage on which it all plays out. In the next part of our journey, we will step outside this single galaxy and see how astronomers realized there were many others, and how that discovery opened the door to an even bigger story, a universe that is not static but expanding. For most of human history, the Milky Way was the universe, a hazy band across the sky, a scatter of bright stars, and a few mysterious fuzzy patches were all anyone could see. Even when telescopes arrived, those fuzzies stayed stubbornly blurry. Some showed spiral patterns. Some were just smudges. Were they small clouds of gas inside our galaxy or enormous systems far beyond it? The answer would completely redraw our map of reality. In the 1700s, a French comet hunter named Charles Messier began stumbling on these imposters. He kept finding faint, glowing blobs that looked like comets at first glance, but did not move like them. To avoid wasting time, he created a list of these confusing objects. That list is now famous as the Messier catalog. It includes star clusters and what he called spiral nebulae, objects like M31 and M51. Messier did not know what they were, only that they were not comets. Over the next century, bigger telescopes revealed more structure. Some nebulae looked like whirlpools. Others were smears with bright cores. Astronomers split into camps. One group argued that these spirals were nearby gas clouds inside the Milky Way. Another group proposed something bolder. They suggested that spiral nebulae were island universes, their own galaxies, each one made of countless stars and lying far beyond our own. The problem was distance. No one knew how far away they were. Without distance, guesses about their nature floated free. The key to solving this came from a quiet, painstaking project at Harvard College Observatory. There, early in the 20th century, a researcher named Henrietta Leavitt studied variable stars in the small and large Magellanic Clouds, two companion galaxies visible from the southern hemisphere. She focused on a special class of stars called Cepheid variables, whose brightness rises and falls in a regular rhythm. By measuring many of them, she discovered a simple pattern. The longer a Cepheid takes to complete one bright dim cycle, the more luminous it truly is. That discovery turned Cepheids into cosmic yardsticks. If you know how bright a Cepheid really is, and you measure how bright it appears from Earth, you can work out how far away it must be. First, you time the period of its pulsation. From that period, you infer its true luminosity using Leavitt's relation. Then you compare that luminosity to the light that reaches your telescope. The difference tells you the distance. For the first time, astronomers had a reliable way to measure vast interstellar and even intergalactic scales. Enter Edwin Hubble, working with the huge 100-inch telescope on Mount Wilson in California in the 1920s. Hubble pointed this instrument at the Andromeda Nebula, known today as M31, which many still thought was a nearby cloud of gas. On long photographic exposures, he resolved the nebula into countless individual stars. Among them, he spotted tiny points that waxed and waned in brightness. They were Cepheids. Using Leavitt's period luminosity relation, Hubble calculated how far away those Cepheids had to be. The answer was staggering. They lay well beyond the estimated size of the Milky Way. That meant the Andromeda Nebula was not a small swirl inside our galaxy. It was a galaxy in its own right. An enormous stellar system comparable to the Milky Way in size, shining across millions of light-years of nearly empty space. The spiral nebulae were indeed island universes. This result settled what astronomers had called the Great Debate about the nature of spiral nebulae. It also exploded our sense of scale. The Milky Way went from being the cosmos to being one galaxy among many. Soon it became clear that the sky is filled with galaxies, from graceful spirals to bloated ellipticals and irregular wrecks, each containing hundreds of billions of stars. The universe had become far larger and stranger than anyone had suspected. Hubble did not stop with distances. He and other astronomers also measured how the light from these galaxies was shifted. When you break starlight through a prism, you see dark lines where atoms in the gas absorb specific colors. In most distant galaxies, those lines are displaced toward the red end of the spectrum. This redshift is a sign that the galaxies are moving away from us, stretching the light waves as they go. By combining redshift measurements with distances from Cepheids, Hubble noticed a pattern. The farther away a galaxy was, the faster it seemed to be receding. Plotting velocity against distance gave a nearly straight line. Nearby galaxies moved away at modest speeds. Distant galaxies raced away much faster. This relationship became known as the Hubble law. It implies that space itself is expanding. Galaxies are not simply flying through a static void. The void is stretching, and they move apart as a result. The slope of that line is the Hubble constant, a number that tells us how fast the universe expands at large scales. Hubble's first estimate was high because he did not yet know that there are different types of Cepheids with slightly different brightness relations. As measurements improved, the value settled lower. A typical modern figure is that for every additional 3.26 million light-years of distance, a galaxy recedes about 65 kilometers per second faster. The exact number is still being refined, and small disagreements about it today hint at deeper questions about the cosmos. An expanding universe changes everything. Run the first movie forward and galaxies move farther and farther apart. Run it backward and they come closer together, eventually reaching a hot, dense early state. This is the foundation of the Big Bang picture, where the universe evolves from a compact beginning into the vast, cooling, structure-filled cosmos we see today. The Milky Way becomes one participant in a much larger drama, growing and changing inside an expanding space-time. Yet even as we think about trillions of galaxies, we study them by starting with one. The Milky Way is special for us not because it is unique, but because it is the only galaxy whose stars we can examine in such detail one by one. Its structure and history are a template for others like it. In the final part of our journey, we will bring all of this together, tracing how the Milky Way formed, how it has grown by devouring smaller galaxies, and what will happen billions of years from now when it collides with its nearest giant neighbor, Andromeda. To really know a galaxy, you have to do more than measure its size and map its arms. You have to ask the same questions we ask about ourselves. Where did it come from? What has it been through? What will it become? The Milky Way is not a static stage where the universe plays out. It is a character with a past and a future. Our entire species lives inside one chapter of its biography. Roll the clock back almost all the way. After the Big Bang, the universe was hot, dense, and nearly uniform. Over time, small wrinkles in that smoothness grew under gravity. Regions that were a tiny bit denser than average pulled in more matter and became even denser. Some of those overdense seeds would one day grow into galaxy clusters. Others grew into individual galaxies. The early Milky Way began as one or more of these seeds deep in the young cosmic web. The first stars to light up in those regions were very different from the Sunday. They formed from almost pure hydrogen and helium, with virtually no heavier elements. Astronomers call these hypothetical objects population 3 stars. They were probably extremely massive, short-lived, and bright. In only a few million years, they burned through their fuel and died in violent explosions, forging the first heavy elements in their cores and scattering them into space. Out of the enriched gas that followed, new generations of stars formed. Some clustered into compact globular clusters, dense spheres of hundreds of thousands of stars. Many of these now orbit in the halo of the Milky Way. Their ages, up to 13 billion years, tell us that the skeleton of our galaxy was already beginning to assemble not long after the Big Bang. At that stage, the system was more like a lumpy, slowly rotating cloud than a flat spiral. As time went on, the growing protogalaxy gathered more and more gas from its surroundings. Because of the conservation of angular momentum, any slight spin in that gas became amplified as it fell inward. The cloud flattened into a rotating disk, like dough spun on a baker's hand. Within that disk, fresh waves of star formation ignited, especially where spiral density waves compressed the gas. This is how the familiar thin stellar disk and its arms emerged from a once roughly spherical swarm. Our galaxy did not grow in isolation. It fed on others. Cosmological simulations and detailed surveys of stars show that the Milky Way has merged with many smaller galaxies over its lifetime. Streams of stars that do not quite match the regular disk orbits are the fossils of those victims. One particularly large ancient merger event has been nicknamed Kraken. It seems to have occurred roughly 11 billion years ago and may have contributed a significant fraction of the present-day halo. The process continues even now. The Milky Way is currently cannibalizing the Canis Major dwarf galaxy, a small, disrupted system whose stars are being stretched into long arcs that wrap around our disk. Other dwarfs, like the Sagittarius dwarf galaxy, show similar signs of being torn apart. To build a spiral as massive as the Milky Way, you do not simply form stars from smooth gas. You also swallow your neighbors. Every star you see in the sky may carry a memory of which ancestral fragment it once belonged to. On still larger scales, the Milky Way is a member of the Local Group, a small cluster of galaxies dominated by two giants, us and Andromeda. The two are bound together by gravity, even though the overall universe is expanding. Right now, the Milky Way is moving toward Andromeda at a speed of about 250,000 miles per hour. That sounds fast. Yet across the gap of more than 2 million light-years, it is a slow approach, the drawn-out fall of two massive skaters spiraling together on the ice of space-time. In roughly 4.5 billion years, simulations suggest that the Milky Way and Andromeda will collide, not in the sense of two solid objects smashing, but as two enormous, mostly empty systems passing through each other. Their disks will interpenetrate. Tidal forces will stretch out long tails of stars. Gas clouds will crash together, triggering furious bursts of star formation. On the sky of any surviving worlds, the night would be filled with tangled arcs of light, entire galaxies streaked across the darkness. Despite the drama, the chance that any two individual stars will collide is tiny. The spaces between stars are huge compared to their sizes. Our solar system will almost certainly sail through the melee intact, though its orbit around the combined galaxy may change. Over a few billion years, the central supermassive objects of both galaxies will spiral toward each other, radiate gravitational waves, and eventually merge into one even more massive core. The final product is expected to be an enormous, smooth, elliptical galaxy rather than a graceful spiral. Sometimes people call this future system Milky Way. What about Earth during all of this? Here, the Sun, not the galaxy, sets the schedule. In about 4 billion years, the Sun will be significantly brighter than it is today. Long before it swells into a red giant, its increased luminosity is likely to drive a runaway greenhouse effect on Earth. Oceans will boil away. The surface will become more like Venus, scorching and hostile. Complex life, if it still exists then, will need to have found a new home long before the Milky Way and Andromeda complete their dance. Later, around 7 to 8 billion years from now, the Sun will exhaust the hydrogen in its core and expand dramatically. It will become a red giant, engulfing the inner planets and probably Earth itself. After shedding its outer layers as a glowing planetary nebula, the Sun will shrink into a white dwarf, a hot Earth-sized ember, slowly cooling over trillions of years. By then, the galaxy itself will have changed shape. The beautiful spiral we know today will be a memory written in the motions of long, settled stars. There is something both humbling and oddly uplifting in this story. The Milky Way began as a tiny wrinkle in the early universe, grew by swallowing smaller galaxies, formed stars that forged heavy elements, and eventually gave rise to at least one world where atoms learned to think about all of this. Our moment is brief, but it is real. We live in a calm suburb of a spiral galaxy that is still evolving around us. When you look up at the night sky, you are not just seeing random points in a dark dome. You are seeing pieces of a grand biography, halo stars that remember the youth of the galaxy, spiral arms where new stars are being born, the faint glow of a disk that is slowly drifting toward a future collision. Somewhere out there, above the crowded center, a supermassive object spins in darkness, holding everything in its grip. And somewhere out here, on a small, rocky planet in a modest arm, a curious species is trying to write the Milky Way's life story before our own chapter ends.